Welcome to AI Frontiers, 220 machine learning papers in 48 hours. In this episode, we explore the latest developments from the computer science machine learning category, or cs.LG, as of November 2025. Join us as we unpack breakthroughs shaping the future of artificial intelligence, spotlight key insights from privacy to explainability, highlight a paper of the day by Xu and colleagues. This is your portal to tomorrow's innovations, today. Did you know that over 200 new machine learning papers can appear on the arXiv preprint server in just 2 days? Each paper may contain a transformative idea capable of shifting how we live, work, or understand the world. This output represents the collective effort of thousands of researchers, each racing to solve the next big challenge in artificial intelligence. The research published today could become tomorrow's headlines. Imagine being able to absorb these breakthroughs before they become widely known. This is the opportunity AI Frontiers provides. The pace of progress in AI can be overwhelming, but AI Frontiers is here to help. In this episode, 220 papers from the cs.LG category have been distilled to identify the main themes shaping the field. These include privacy, fairness, efficiency, and more. Whether you are a researcher, practitioner, student, or a curious mind, key ideas and the people behind them are spotlighted. The aim is to unravel the stories and challenges driving artificial intelligence forward, providing both context and clarity. What exactly is machine learning? At its core, machine learning refers to computers learning from experience, enabling them to make predictions, recognize patterns, and improve over time without explicit programming for every scenario. The field stands at the intersection of statistics, optimization, computer science, and domain knowledge. It can be thought of as the nervous system of modern AI, constantly sensing, adapting, and responding in real time. The cs.LG category encompasses broad, interdisciplinary innovations. A central technical concept is generalization. Models are trained to learn patterns instead of merely memorizing data. The first theme is privacy and fairness. As artificial intelligence enters sensitive domains such as healthcare, finance, and social services, the risks associated with privacy breaches and algorithmic bias become acute. Differential privacy serves as a locked diary for data, ensuring that individual information is protected while still enabling useful learning. Fairness auditing frameworks have been developed to ensure humans remain integral to the process. For example, the DP-PMLF method by Xu and colleagues provides a mechanism for safe learning. The challenge is akin to tightrope walking, balancing privacy and accuracy without falling to either extreme. A second prominent theme is physics-informed and domain-embedded learning. In this approach, models are guided not only by data, but also by the foundational rules specific to their domain, such as the laws of physics. Neural operators are employed to efficiently solve complex equations. A notable example is the AC optimal power flow problem, addressed with homotopy techniques by Wang and colleagues. Homotopy refers to gradually transforming a simple problem into a more complex one, making learning more manageable. This can be likened to a GPS that navigates by understanding both the visible roads and the underlying traffic laws. The third theme centers on self-supervised and unsupervised learning, which are increasingly important as the majority of available data remains unlabeled. Self-supervised models learn by mimicking the way children observe and infer rules on their own. The LeJepa framework, introduced by Chen and colleagues, is an example that delivers robust and stable representations without reliance on external labels. Advances such as joint embedding and contrastive learning further propel the field. The metaphor here is akin to learning the rules of a game by observing others, rather than relying solely on direct instruction. Research insights come alive as stories from the front lines. Xu and colleagues' DP-PMLF method demonstrates how privacy and accuracy can be balanced steadily. Wang and colleagues use homotopy techniques to guide models over steep optimization cliffs in power grid management. Chen and collaborators introduce LGEPA, removing the training wheels from self-supervised learning for greater stability. Techniques like pruning and regrowth, detailed by Li and colleagues, yield smarter, leaner models. Finally, Singh and colleagues present ProtoScore, a framework for measuring model glassiness or transparency, enhancing trust in AI systems. Focusing now on the paper of the day by Xu and colleagues, titled Enhancing DPSGD via Per-Sample Momentum and Low-Pass Filtering. This work addresses the long-standing trade-off between differential privacy and model accuracy. Differentially private stochastic gradient descent, or DPSGD, typically disrupts learning by introducing random noise. The central question explored is whether it is possible to smooth out this noise while still protecting privacy. The result is DP-PMLF, a dual approach that advances both privacy and performance. Imagine a balance between noise and accuracy, achieved through innovative algorithmic design. DP-PMLF operates through two key mechanisms: per-sample momentum and low-pass filtering. Per-sample momentum assigns each data point a personalized push, enabling more stable and individualized updates during training. After privacy-preserving noise is applied, a low-pass filter is used to clean up high-frequency artifacts, smoothing out the residual noise without compromising underlying privacy guarantees. This is analogous to giving each student in a classroom a tailored boost, then filtering out distracting background noise. The result is models that converge faster, require less data, and achieve higher accuracy. Low-pass filtering, in technical terms, removes the unwanted jitters from the learning process. The impact of DP-PMLF is significant. The method has been rigorously verified both theoretically and across real-world benchmarks. Its adoption enables artificial intelligence to be deployed in high-stakes fields, such as medicine and finance, where trust and privacy are paramount. The motivation driving this research stems from genuine concerns about data privacy and the desire to ensure that practical privacy does not come at the cost of scientific or technological progress. This is a human story, one about building trust into every algorithm and ensuring AI benefits all. Looking toward the future, the evolution of machine learning resembles a river branching and merging as it flows toward an ocean of possibility. Human-AI collaboration is expected to deepen, with frameworks emerging that keep humans engaged as collaborators and co-creators, not just overseers. The fusion of machine learning with domain-specific expertise across fields like physics and medicine will yield new breakthroughs where data alone is insufficient. Continual learning will enable models to adapt as the world changes. Yet, the balance between privacy, fairness, and utility remains a persistent challenge. Imagine a river's journey, carrying knowledge forward through streams of theory, practice, and human values. The key takeaway from this exploration of 220 papers is that machine learning is maturing. The field is becoming more nuanced and increasingly focused on real-world impact. It is not solely about maximizing accuracy, but about building models that are fair, private, trustworthy, and efficient, ready for the complex challenges of our era. Innovations by Xu and others are paving the way for practical solutions. The journey is only beginning. And your insights matter. Listeners are encouraged to delve deeper, share their thoughts, and participate in this unfolding narrative. The synthesis presented in this episode was created using advanced tools for summary, visualization, and text-to-speech synthesis. Summaries were processed with the assistance of GPT 4.1, while visual and TTS outputs were generated using capabilities from OpenAI and Google. Each episode is reviewed by human experts to ensure rigor and transparency, though minor oversights may remain. For further details and references, listeners are directed to consult the episode notes. The guiding principles for AI frontiers remain transparency and academic rigor. To stay updated with the latest in AI research, subscribe to AI Frontiers for weekly deep dives and insights into the most recent breakthroughs. The channel is dedicated to keeping you informed about the evolving landscape of artificial intelligence. Your feedback directly shapes the direction of future episodes. Let us continue exploring the edge of AI together. In this podcast, we bring you the latest breakthroughs in computer science and AI. Straight from arXiv preprint server, from neural networks to quantum computing, complex research is made accessible so you can stay ahead. Whether you are a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv preprint server.